Here's another video about engineering myths and lies. I love uh, sharing them when I have to. One of them is the concrete's weak in tension. Weak in tension. Always 10% rule, pretty much. 10%, and don't even count the value most of the time. But I'm going to tell you, the split test that's done. It just puts concrete under compression again. This is more the tensile strength, tension ability of a test sample of concrete. I say test sample because I don't believe a formula can be extrapolated from the small sample, which a formula does exist, from the small sample to extrapolate out to larger spans. I don't believe it. I don't believe that that works. This is stubby. It's going to behave differently than a larger span section of this. Say this is only 3 foot. Now you put that same sample at 6 feet, it's going to behave differently and fail sooner. The closer you get these supports to each other, the more this acts as a column capacity. It is a flexural test. This will be a shear test, tension test, correct? Yeah, I said shear test out here. Tension test, its flexural ability. It's already failed. It's at 28 kilonewtons, approximately 29 kilonewtons. If you need to know what that is, you come over to a scale. You can type in 28 kilonewtons. I like converting to ton force, and I don't have to do any more fancy conversions. It's 2.8 tons based on this loading. This loading has 2 bars, continuous loading across it with that much surface area. I have no idea how much surface area that is. And let's just tap the screen a couple times. You'll see the fracture is actually diagonal from our view going this way, and a fracture at the bottom. The needle bounces down to 0 once the fracture happens because the pressure is released. And there we are there, the pressure on the load cells. You see here the fracture. Let's go back. All I'm looking at is a gauge. You can look somewhere else if you like. As long as I see the needle go up, I know I'm still climbing. It might be already in fracture mode because I don't see the needle moving. Let's go back a couple of frames. Here we go. Looks like about 29 kilonewtons. So 2.9 tons. More than that. 29 kilonewtons might be 3. Yep. 2.95 tons, which is 6,000 pounds of force. Wait a minute. This is only probably 3,000 or 4,000 psi concrete. So 10% of that is 400. Let's say 400 psi. Then the surface area. You can play all the games you want with that, running around trying to extrapolate. It doesn't extrapolate out. The larger the span, the more it will fail at a lesser weight because of its own dead weight, and it's trying to act like a cantilever. The longer span is without the reinforcement in it. This is non-reinforced. There's no rebar added, no wire mesh, no fiber, nothing like that. And here we are, way up there at this much force to fracture this concrete sample. But this should be failing at way down there at 400 psi. 400 psi. So let's convert this to 29 kilonewtons to psi. Let's see. And nope, this won't change out like that. Sorry, I won't do that right now. It's a calculation anyway of the surface. So just want to show you that this took 3 tons of force, and that was tension. 3 tons of tension force, 6,000 pounds of force to fracture this. Now it was shared on two points. So I don't know how you would divide that up because I see the fracture there. I like a single point loading. Would have been better. This would act like single point loading, you would think, because it both cuts down at the same time. Not true. They create their own friction against each other as this goes down. The friction here, and these two create a different torque in it. I like a single. And that way, and you can see it better, but it's not reality because this would be strapped down, tied down, and the forces would be okay. The forces are explosive in this small sample. In a larger sample, we see that if you look at these and really dive into them, you'll see the deflection up on these things are a lot. And that's not true to nature. It's natural location. And there's the fracture. Just abrupt. Just abrupt fracture. You can watch the gauge right here. Okay. You see it flexing? No, you don't. It's internal force, and it's just holding it back, and it's going to be abrupt, just like a cable would break on a bridge. Just like a cable would break, just abrupt fracture, and wildly the cable goes into the air. Same thing with this. Just that. Seems like nothing, but it was 29 kilonewtons on there. That was a lot of force on there. And the fracture happened here. You can see their rollers rotated a bit, rotated up. Their rollers, they're non-pin connections. Okay, what else do I want to say? So the thickness of this, the location, they're equally spaced. So, it looks like it's on an angle. It is 100% equal, very accurate on its spacing. The sample it's cured. I've already dived into this many times, this content. It's cured in a shop, so it's an environment that you get consistency. And you won't get that in a real field. But again, this is the tension. Showing tension is the concrete is not weak in tension. There's no reinforcement in here, short of, the mortar and the bond of the concrete. That's the reinforcement. But there's no added reinforcement, no rebar. Yet that's the sample, which you cannot extrapolate out. I swear you can't extrapolate out. That no matter what formula you're using, it doesn't work. So in spite of the error, the formulas are working in spite of, well, they're not really working, are they? We're getting a lot of punch shears and failures all around the world. So obviously the calculations, or people are just making errors one after another. My point again, that's 6 tons of force. 6 tons. It's not 10%. It's not 10%. Okay, take care. Do the math. Say that's 4,000 psi. Use the 10%. This is 6 inches tall. Can you do the math? That's 24 inches. 24 by, I think this is 7. Something like that. 150, roughly 150 square inches. 150 square inches. But remember, not all of it will be under the surface area. Not all will be in tension. Whatever the neutral axis is, when as the load progresses, neutral axis changes, and you're getting that much is taking the tension. So you can't extrapolate that the whole shebang is in shebang. That's a technical word. Is in tension. Some of it is in compression up near the top. So not all of the cross section you can calculate. All right. Hopefully this wasn't too confusing. I'll back it up with some more, but this is good data to back it up for you guys. I have more to come.